Okay. Hello, everyone, and welcome to another online causal inference seminar. We are very happy to have Iván Díaz here with us today from New York University. Iván will talk to us about recanting twins, addressing intermediate confounding and mediation analysis. Iván will have a collaborator in Q&A. After Iván's talk, we will have Daniel Malinsky from Columbia University as our discussant. So welcome both. Questions today will be held by Razia.
Thanks, Georgia. Yeah, so as before, please submit your questions as soon as you have them and put them in the Q&A. And if there are quick clarification questions, I'll interrupt Iván. Otherwise, he will have natural stopping points to get to your questions. And so without further ado, I'll hand it over to Iván. Iván, please start sharing your screen.
Thank you. Sorry, my slides were up, but I don't see them anymore.
I kicked you out for a sec.
Yeah.
So
yeah, let me just try to find them again. I think when you go full screen, they get lost. There we go.
Looks great.
Excellent, great, thank you. Thank you. Yeah, so thanks so much for inviting me. I'm happy to be here. This is joint work with Tang Vo, Nick Williams, Richard Leon, Kara Rudolph. Tang, I think he's in the audience. He does not know that he's going to be answering questions. But if there is any questions, Tang, that you can answer, that would be great. Yeah, and so a lot of this work is actually, I just want to say a lot of this work is Tang's work. We've been working together in this project for a while. So yeah, just to highlight that. Okay, so the goals of the talk are as follows. So I'll start revisiting actually just two of the most widely known methods for mediation analysis. And I'll discuss a little bit about their strengths and their shortcomings. In mediation analysis, there is this very important issue of intermediate confounding. So I'm going to talk about what that is and what are the implications of having intermediate confounders. Then I'm going to move on to proposing new methods that address some of the shortcomings of these two existing methods that I'll discuss. And in the process of doing this, we'll talk a little bit about philosophical issues in mediation analysis related to manipulability of causes, to the falsifiability of conclusions learned from a mediation analysis, etc. And a caveat at this talk, I mean, there's a lot of conceptual and definitional issues in mediation analysis, so the talk will be mostly conceptual. We won't actually get time to talk about estimators or numerical studies, applications, etc. All of that can be found in the papers that the talk is based on. So let's start with a DAG. The main goal for the talk will be to investigate the role of a mediator M in explaining the causal effect of a binary treatment A on an outcome of interest Y. And the general sort of model that we're working under can be represented by this DAG, where we have some set of baseline pre-treatment confounders W, and we have some intermediate confounders Z, which are affected by the treatment, right? So these are variables that confound. Z are variables that confound the relationship between the mediator and the outcome that are themselves affected by treatment. In some of the discussions some of the points that I will make, I'll use a modified version of an example that was discussed by Robbins and Richardson in 2010, where we're looking at the effect of smoking on myocardial infarction and how that effect is mediated by hypertensive status, where the modification to the example is that I added an intermediate confounder Z, vasopressin. Vasopressin is a hormone that has a lot to do with, I mean, I'm not a doctor, but this hormone has a lot to do with your blood pressure, and so it's important when studying hypertension, and it's also affected by smoking status. We'll talk a little bit more about that. So some preliminaries before I start talking about the definitions. Later in the talk, I'll introduce an additional 2 causal models. But to begin with, in the first part of the talk, I'll be using this what I call a standard structural causal model. So we're basically going to assume that the model M1 is a tuple where we have some variables U, which are exogenous and are unmeasured, some endogenous variables X, which are measured, some functions F, a collection of functions F. I'll tell you in a bit what these functions are, and a model P, a set of allowed distributions for the exogenous variables. And so the endogenous variables are the variables that you saw in the DAG before, the W, A, Z, M, and Y. The exogenous variables are a set of errors, so-called errors, each one associated to one of the endogenous variables. And then we have a set of functions F, again, one for each variable. They're deterministic, and they're functions such that we assume that the data is generated in this way. We assume that W is generated as a deterministic function of its corresponding exogenous variables, and then A is generated as a deterministic function of W and its corresponding and exogenous variables, etc. That we continue like that in the variable ordering until we generate Y as a function of all the past variables and its error. So we're actually going to use this model to define counterfactual variables, and so we'll be working with variables of these three types, basically on their interventions only on A, interventions on A and M, and interventions on A, Z, and M. I mean, these are not the only counterfactuals we'll see. We'll see various types of counterfactuals like this, but I'm just mentioning these three just to get a sense for the kinds of quantities that we will define. And I'll stop, not stop, but I'll make a clarification here that I'm actually, and I actually think these types of variables can have multiple alternative interpretations. And I'm here in this slide showing you two of those alternative interpretations. So in the left column, we can think of the sort of standard interpretation of the counterfactual YA, which would be, the outcome the counterfactual outcome that we would have observed in a hypothetical world where we performed an intervention and where we set the variable A equal to little a, right? So that's sort of the standard interpretation of a counterfactual variable. And then a second interpretation that I think is important, particularly in mediation analysis, because a lot of the variables that we talk about when we're doing mediation analysis are not manipulable, like the mediators are often not manipulable. But you can have an alternative interpretation of counterfactual variables like this one, right? Like this, the interpretation in this column, where you're actually not intervening on A to set it to any level. You're allowing it to take the value that it would have taken naturally without an intervention. But you're intervening on the way that you're generating the outcome variable, so Y sub A. To give you an example, if A was, say, a variable like race, right? So, and to simplify things, let's say we're talking about just a binary variable where we have some reference level for race, for example, say white, right? And this little a is actually equal to white, right? So this counterfactual variable in that world would have been the outcome of a person had we modified the mechanism that we use to assign that outcome to be the mechanism that that the world uses to assign the outcomes of white people, right? So it's not conceptualizing, like, the point I want to make in this slide is that to think about counterfactuals, you don't need to conceptualize interventions on the variables themselves, on the variables that you're assuming are the cause, but you can think of interventions on the mechanisms and on structure. And I'm citing here a paper by Dan that actually talks about this in a slightly different way, but maybe Dan can tell us a little bit more about that later. So some advantages of these two types of interpretations. Well, the first one is more policy relevant. It tells you what actions to perform, so it's prescriptive. It's useful, of course, for manipulable causes. The second interpretation is more scientific relevant, like it tells you what's happening mechanistically in the counterfactuals, and you can use it for causes that are non-manipulable, as I said before. And again, I think this is important. Specifically, these two different views of counterfactual analysis are important for mediation analysis, because mediators are often non-manipulable. Okay, so with that, then we can start thinking about mediation analysis. How do we conceptualize mediation analysis? The most, I think, natural, pun not intended, way of thinking of defining direct and indirect effects is, or like the most common way of defining direct and indirect effects is what I have in this slide here, is to take the average treatment effect, which would be, you know, a contrast between y1 and y0. Again, whatever interpretation you want to give to these counterfactuals, take an expectation across the population, and then this counterfactual y1 m1 is actually identical to this counterfactual just because of the way the structural causal model is set up. This counterfactual is identical to this one, right? And so we're adding and subtracting here another counterfactual, what we call a cross-world counterfactual. And when we add and subtract that quantity, we get two quantities, one which we call the natural indirect effect and the natural direct effect. And you can see from the definitions that, you know, I'm just revisiting definitions. The natural indirect effect is indirect because I'm contrasting counterfactuals where I'm fixing A for purposes of the direct effect, but I'm allowing A to vary for purposes of the effect through M. And a similar interpretation holds for the natural direct effect. I could have defined these direct and indirect effects, you know, using the alternative cross-world y0 m1, but you know, I think that there are interpretational issues associated to that, and you know, whether one or the other one is more relevant, I think, depends on the scientific question. But basically, this parameter hasn't, or you know, it's used in practice, but it has a couple of important, I think, well, one very practical and another one a bit more philosophical issue. The more philosophical one is the assumptions that are required to identify this parameter are not falsifiable through experimentation. That's kind of important because if you do an analysis, then somebody who wants to run an experiment to verify the claims from your analysis cannot do it. And then the second one, which I think is a more practical issue, is that these parameters are not identified when you have an intermediate confounder Z, right? So in the model that we started off with, we don't have identification. So I guess one of the many, there are multiple solutions that have been proposed to this problem in the literature, but one that has become very popular is this idea of interventional, randomized, direct and indirect effects. And so what these effects do is you consider an alternative variable GA, which is a random draw from the distribution of M, A conditional on W, or of the counterfactual. And then you define an alternative total effect, right? You define an alternative total effect where you're also intervening on the mediator to set it to this quantity, to this new random draw from the mediator distribution. So this Y with two arguments denotes an intervention on both the treatment and the mediator variable. And then you do a very similar subtraction and addition to what we did in the previous slide, where you add and subtract this cross. It's not a cross-world counterfactual, but you add and subtract this quantity. And you get a new definition of a randomized interventional indirect effect and a randomized interventional direct effect. I think this approach is sort of what's standard now in practical mediation analysis, particularly in epidemiology. You know, the people use this effect quite a bit. This parameter has a couple. I think this one is less important. I mean, you could argue that this is not really a problem for this parameter, but it has a couple of other, again, practical issues that are important to think about. The first one is it does not decompose the average treatment effect. So it's like where we had to define a different total effect in order to achieve this decomposition. So we're not we're forgetting about our original goal of decomposing the ATE into effects that operate from the through the mediator versus not. And it has another important issue that Caleb Miles sort of brought to light last year, I think, or a couple of years ago when this all started, which is it does not satisfy something called the mediational sharp null criterion. I'll tell you a little bit more about what that is, but it basically means that you can have a setting where there is no unit in the population who experiences mediation, yet the randomized interventional direct effect, the indirect effect is non-zero, right? So it is not really measuring mechanisms that operate through a mediator. So to talk about this sharp null criteria, we sort of need to start thinking about definitions. And so one general definition, for example, for causal influence would be that the variable A is said to have a causal influence on the variable Y if and only if this supremum, right, where I'm taking the supremum over all values of little a1 and little a2, I do the difference, right? So basically, if the counterfactual function varies with A actually with positive probability, right? So that's just a definition where we say, there is a causal influence through, or like a direct causal influence. Likewise, we can define causal influence through a mediator. And then what we're doing is we're fixing A1, right, to any given value, and we're varying the value that gets input into the mediator counterfactual. And if when I take the supremum of all A0, A1, and A2, this supremum is greater with positive probability, then we say there is a causal influence through M, right? So these are just definitions. And so a measure of causal info, or like the causal effect of A on Y through M is said to satisfy the mediational sharp null criterion if it is null whenever there is no causal influence through M. So basically, this is formalizing what I said in words, that you can have for the randomized interventional direct effect, you can have a setting where there is no individual who experiences mediation, yet the randomized interventional effect is non-zero. And again, we also need a definition because in later slides, we're going to do this for every path. So we need for each of the paths that we're thinking about, the paths that go from A to Y, we need a definition for causal influence operating through each path. So in this table, I'm just labeling the paths. So we have 4 paths. We have A through Y, AZ, Y, AZMY, AMY, right? And just gave the names P1 through P4. And here we have the respective conditions so that we can say, that there is some kind of causal influence through each of these specific paths. Where again, I'm varying, what I'm varying here is A1 and A0. All the other ones remain constant, and I'm taking a supremum. And if this supremum is positive with positive probability, then we say there is influence to this path, right? And likewise for all the other paths. So ideally, we will have a decomposition of the ATE into path-specific effects. So we'll be able to, where we're going basically is we'll be able to decompose the ATE into measures of each of these specific paths that satisfy this path-specific sharp null criterion, in the sense that if there is no influence through each of these paths by this definition, then the effects should be 0. So how can we do that? Well, a natural way to do this, again, is to define the natural path-specific effects in complete analogy to the natural direct and indirect effects. And to do so, I have the 4 paths here that I had in the previous table. This order is arbitrary. We can define different orderings and achieve a similar decomposition. But to do that, to define the natural path-specific effects, what we're going to do is we're going to consider 5 counterfactual variables now. This first variable is just y1, where I have set the treatment equal to 1, basically for purposes of everything, every mechanism. The second variable involves one modification, which is I'm setting A equal to 0 here for purposes of the direct A to Y path. Then compared to the previous one in YS2, I'm doing another intervention where I'm setting A is equal to 0 in this counterfactual and so on, until I get the final counterfactual, which is equal to actually Y0, because I have set A is equal to 0 for purposes of every path. And so the way we define, the natural path specific effect through path PI is by doing contrasts, by telescoping these 5 counterfactuals, right? So we contrast this one with this one, then we get a measure of path 1. We contrast YS1 with YS2, then we get a measure of AZ to Y, etc. Right? And so, okay, so that's a nice definition, and we could maybe now proceed to try to find an identification result for this effect, but that won't be possible because, again, we have a similar issue to what we have in the natural direct and indirect effect. The distribution of this counterfactual is not identifiable in the presence of Z. The reason is that, or the name that Avin and Pearl gave to this problem is the recanting witness. The variable Z tells one story for purposes of the path A, Z, Y, and a different story for purposes of the path A, Z, M, Y. And that turns out to be a problem for identification when you do the math. So actually, we cannot disentangle the effects that operate between path 2 and P3 in this, if we were to use the natural path specific effects. So we sort of need to address that, and our proposal is actually taking that idea of recanting twins and saying, what if I can randomize instead the recanting twin in order to achieve have an effect that is actually identifiable. And the way we randomize, the idea is basically emulating a path that sort of transfers the same intervention that was transferred along the original path. So to do that definition, let me define T1. Actually, let me stop here to see just if there is any questions so far, because I'm going kind of fast.
There is a quick clarification question that was way past the point, but it was in slide 5 where you were talking about two systems of equations. So the question is, why do we have the counterfactual MA in the equation for Y, but on the left-hand side, on the right-hand, on the left-hand side, it's MA.
Here? Yeah. So I mean, I'm thinking of these functions at the end of the day really as functions of only the error variables, right? So you can compute what this M sub A would be just as a function of the errors by doing the composing the functions. I just didn't want to add a lot more notation to the slides, but basically what I'm thinking is this is a function of, at the end of the day, it's a function of only the U's, right? The U, UW, UA, UZ, UM. I'm just being lazy and not putting all the notation in there, but the idea is that function of the exogenous errors is the function that is the mechanism that we want to mimic in this counterfactual. Does that answer the question?
I think so. Yeah, thanks.
Yeah. Great. Any other questions? I think that's all for now, right?
That's all for now. Yeah, thank you.
Great. Yeah. Okay. So our proposal then is going to be, we're going to define these variables T1 and T0, which are defined as random draws from the distribution of Z1 given W and Z0 given W. And, this term recanting twin was suggested by Eric Chekin in a conversation with him. So thank you, Eric, for suggesting this. So we define the recanting. So the recanting witness is defined in this way, right? So Z sub A is the recanting witness of Z sub 1 minus A, right? It's the variable that is telling a different story for purposes of the other path. And so what we're going to do is we're going to say T sub A is the recanting twin of Z 1 minus A, right? So basically we use a random draw from the alternative distribution to tell a different story rather than using the original variable. And what this does is it helps us actually achieve a definition for the path-specific effect through path P2 and through path P3, which were the problematic ones, because then what we do is, in the original contrast, we needed to contrast these variables ys1 and ys2, where we had a problem that what we really wanted to contrast was with respect to these two interventions. But we have this recanting twin here, right? This recanting witness, sorry, Z1. And so what we do for purposes of measuring path P2 is that we replace that recanting witness by its recanting twin, T1, right? And we do the same thing when we're measuring P3. The recanting witness here was Z0. So what we do for measuring P3 is we replace that by its recanting twin, T0, right? So it's a random draw. So it's a stochastic intervention on the Z variables. And what that helps us do is actually we're able to achieve a decomposition of the average treatment effect in terms of these 5 sort of parameters. So the first 4 parameters will be parameters that measure the causal effect through each of the 4 paths that we talked about earlier. And we have a 5th parameter here that will turn out to be a measure of intermediate confounding. I'll talk a little bit about what that means in the next slide or next 2 slides. But I think one important first result that we prove is that these 4 path-specific effects satisfy the path-specific sharp-null criterion, meaning, again, they are such that if there is no causal effect operating through the path at the individual level, then these effects are 0. And they also have this nice property that they have the same sign as their natural path-specific effect counterparts. So we're actually recovering both, whether it's non-zero and their sign, the sign of the natural path-specific effects. Yeah, so I said I would talk a little bit about the interpretation of that 5th parameter, and to to talk about that interpretation, we needed to have a very sort of precise definition of what we mean by no intermediate confounding. Here is the definition. I will not go into detail about what this definition says. We'll just say intuitively what this definition says is that there is no individual in the population for which all these direct paths, A to Z, Z to M, and Z to Y, are all active, right? So the idea being that, the paths can be active for some subsets of the population, but they can't be active for any one given individual, because in that case, we would need to adjust for Z. If they are not all active at the same time, Z is not really a confounder and it's not really intermediate, right? So this is just giving you that definition. And so what we have for this parameter, for this 5th parameter in the decomposition, is that under no intermediate confounding, right? If Z is not really an intermediate confounder in the sense of the previous slide, then this and should be deleted. Then what we have is that the path-specific effects, the psi P1 through P4, are actually equal to their natural counterparts, not only at the population level, but also at the individual level, right? So when you look at the individual level counterfactuals, we would be recovering each of the natural path-specific effects in the absence of intermediate confounding. So that's a sort of a nice property of this decomposition. Let me just check. Yeah, another reason why I think this 5th parameter is quite useful is that this parameter will actually turn out to be identified, and you can develop estimators for it, etc. So having this decomposition actually allows you to test explicitly for intermediate confounding by Z, right? So if you have your causal model, you have a variable Z that you suspect might be an intermediate confounder, you can actually, write this, and of course, if all the identifiability assumptions hold, you can actually write out all of these parameters, develop an estimator for this fifth parameter in the decomposition, and test whether it is equal to 0. If you fail to reject the test, then you also fail to reject an interpretation of these 4 parameters as path-specific effects, right? So it may be that they are actually giving you the original target rather than this randomized target. So we actually think this has, like, this can be quite important in mediation analysis. So, okay, having achieved the decomposition, let me again stop there. I think there are no questions, right?
No, you're good.
Great, thanks. So having sort of talked about the definitions and talked about the properties of these definitions, let's move on sort of to the natural next step in causal inference, which is to talk about identifiability. And so for identifiability, we'll need what has become now standard in this kind of problem, sequential ignorability. I will say we need sequential ignorability also of the relationship between A and Z, just because we're also doing interventions on Z as on the intermediate confounder, the recanting witness. So basically, we need W to contain all common causes of A, Z, M, and Y, of A, Z, and M, and of A and Z, right? So standard sequential ignorability. The assumption that is a little more problematic is this fourth assumption, this cross-world assumption, where we're actually requiring independence of 2 counterfactuals, but these counterfactuals are indexed by distinct interventions, right? So that's this assumption is often the one that's considered problematic in mediation analysis, because you cannot test it by running an experiment, and therefore you cannot refute the conclusions that you achieve from a mediation analysis. I will say one thing, a note, which is this: unlike the assumption required for the natural, direct, and indirect effect, this assumption also this independence is defined also with respect to 2 counterfactuals that intervene on Z. And therefore, even though it is a cross-world assumption, it's not the same cross-world assumption that we had for the natural direct effect and natural indirect effect. And therefore, it can be satisfied in the presence of this intermediate confounder. I think I'm missing a couple of, sorry, this may be the wrong version of the slides. Sorry. Yeah, okay. Let me continue, and I'll make the point later. So anyway, under these 4 assumptions, we have these identification formulas. They're kind of ugly looking, but they don't have anything that we wouldn't expect there, just expectations of the outcome, conditional on all their past. And then for each of the counterfactuals, you're marginalizing Z and M using different kind of probability functions. I mean, they're not the nicest statistical functions actually to study or to estimate. We're in the process of actually trying to construct general estimators for these functionals, but there are statistical functionals that in principle can be estimated. Let me stop there. I think there is a question.
Yeah, on slide 15, so they say given the decomposition, can the average total effect be 0 while the other side cases are non-zero? So they sum to 0. If it is allowed, does it induce any further challenges?
I don't, let's see. I don't think I follow. Can the AT be 0 while the other are non-zero but sum up to 0? Yeah, I think that's I actually let Tang answer that question. I think he said he'll answer it in the comments.
Okay, the question was flagged as live, and but otherwise we can skip.
There is another question. Is there any relationship to single world intervention graphs? There is, yes. I'll talk a little bit about that later. But actually, I mean, I don't know if Tang is answering, but the answer to the first question about slide 15 is that doesn't introduce any chalices. You can still have effects that cancel out through each of the paths, and the ATE will be 0, and that doesn't introduce any problems. I think that's the standard issue of what do they call it? Inconsistent mediation. And it can happen here as well, and it wouldn't be a problem. Great, thank you. So okay, so let's move on. There were mainly 3 issues that we wanted to address when we started the talk and the project, really. The first one was we were trying to think, okay, can we achieve a decomposition of the average treatment effect into path-specific effects? And I called that done, although with a yellow check mark, because the decomposition is not perfect. We have that 5th term in there that is sort of a measure of intermediate confounding. It's not quite a perfect decomposition into path-specific effects, but at least we have something that is both interpretable and measures the effect through each path. The decomposition must satisfy path-specific sharp null criteria, and we saw we have a result that proves that that's the case. And this third one, which actually we haven't talked about, and it's the one that is related to SWIGs, this identification, the identification assumptions could be tested through experimentation so that scientific theories can be falsified. And this is not quite the case in the models that we have discussed, because identification required this cross-world assumption, which can be tested by experimentation. And so I guess in recent years, maybe in the last 15 years or so, there has been a growing literature on these so-called separable effect models. And I'm going to discuss sort of the relation between what we are proposing and these separable effect models. Basically, you know, the upshot is that these parameters will have an interpretation in a specific separable effect model, so that we can change the assumption, we can change the cross-world assumption for an assumption of separability of effects. So to talk about separable effect models, let's go back to the example that I was discussing at the beginning of the talk, where we have A is smoking, M is hypertensive status, Z is vasopressin, and Y is myocardial infarction. So the main idea of separable effects is that if we can take the treatment A and decompose it, understand which components affect Z, M, and Y separately, then we can write an alternative causal model, a different one from the one I started with, that incorporates this additional assumption. One conjectured, separation of these effects would be, let's say we have A is now a vector with 3 components, where we have AZ denotes whether the nicotine is delivered to the hypothalamus, where vasopressin is synthesized, and therefore, this is the direct impact of smoking on vasopressin Z. AM denotes whether nicotine is released to all other organs, and AY denotes the presence of any other sort of cigarette toxins that might impact myocardial infarction. So this is an example of how you would separate, or like how you would think about these separable effects. And so if you have that kind of information, if you can actually posit these ideas, then you can actually modify you can think of an alternative causal model where you include this information, right? So in this causal model, which I'm now calling M2, we have similar components. I'm using the same notation, but this wouldn't be the same functions specifically if you have a separable effect model. But basically, we have U, X, F, and a probability distribution for the errors, where now the effect of A on Z is actually written in this way, right? So you first, you extract the separable component from A that operates on Z, and that's what gets input into the function, right? And same thing for AY, and same thing for AM, right? This is, by the way, my formulation of separable effect models, our formulation. This is not the way they were originally posited. The way they were originally posited was using just counterfactuals as the primitives, not a structural causal model. But so because we're also performing interventions on Z, the path-specific effects that we propose will also require us to make assumptions about the separability of Z in the structural causal model. And so the model that I'm going to talk about in the slides in the paper, we do have results for both of these models, but in what follows, I'm just going to focus on this model M3, where I'm assuming that the effects of Z are also separable, right? The effect of Z on M and the effect of Z on Y is also separable. And so again, we have to assume that AZ, AM, and AY are deterministic functions, and they're known, and also ZM and ZY. And if I could start conjecturing what this variable ZM and ZY could be. For example, I could say ZM denotes the vasopressin that's released in the circulatory system so that it can have a chance to affect hypertension by increasing blood pressure through vasoconstriction, etc. And ZY could be the vasopressin that's released directly into the brain, which has been linked to social behavior that can increase stress, and therefore increase the likelihood of myocardial infarction. So in that model, in this model M3, we're actually able to replace that cross-world assumption by a series of single-world counterfactual independencies, and this would be the relationship with Swigs, right? We would be able to write these assumptions in using a Swig. I'm not going to go through this, but if you want to go through the paper and convince yourselves that all of these assumptions are actually single world and testable, you're welcome to do that, and we're happy to answer questions. I will say one thing, which is how you can actually test, for example, for this assumption in a randomized experiment, which is as follows, right? So this is the assumption that we have. We have this counterfactual, which is indexed by interventions on the separable components AY, ZY, and on the mediator, and this counterfactual, which is indexed by, again, interventions on the separable components AM, ZM, and AZ, right? So we can consider an experiment G that actually takes all of these separable components of A and Z and randomizes them, right? But we're not necessarily randomizing ZY because ZY is in this, we need it to be a random variable, right? So we randomize AZ, AM, AY, and ZM, right? And so, conceptualizing this type of experiment would require you to assume that it is possible to randomly assign patients to get nicotine delivered directly to the hypothalamus, nicotine directly delivered independently to all other organs, and smoking a nicotine-less cigarette AY so that you get all of the other toxins from cigarettes into your bloodstream, into your system. And we would also be able to have an experiment where we can randomize vasopressin release in the circulatory system, but not randomize it or not make any modifications to vasopressin released to the rest of the organism. So you can see how this is actually quite a complicated experiment. It's unlikely that that we'll have the technology to do this kind of experiment or even ethical reasons to do this experiment anytime soon, but this is the type of experiment that you would need to conceptualize. So in that experiment, we have identification of this probability distribution, the probability distribution of this conditional on all of this in terms of this function, and we can actually go and estimate this function. And if it varies with M or ZY, right here, M or ZY, if this function varies with these two arguments, then we can refute and we can reject the hypothesis that this assumption holds, and therefore, actually test the single world independencies. A very practical sort of note on these identification assumptions. There's a set of assumptions on the errors given here that are sufficient but not necessary for all of the above assumptions that I discussed to hold, including the cross-world assumption, right? So what are these assumptions saying in sort of practical terms that somebody who's trying to do a practical mediation analysis can understand? What this is saying is W is a variable that contains all common causes of A and Y, M, and Z, right, together. So it's I'm labeling this assumption as the non-measure confounder assumption because it has that standard sort of interpretation in the way people think about a measure confounders. So my take on this mediation analysis is that in the absence of knowledge about the separable components of A and Z, the best bet to identify path-specific effects is actually to ensure that this is to make every effort to ensure that this assumption holds, in the sense that you have non-measure common causes of M and Y, of A and M and Y, and all of the combinations between A, Z, M, and Y. And of course, we have results for this in the paper. In the paper, where we're tackling only the model where effects of A are separable, but I did not discuss those in here. So I think I'll stop there. These are the two papers that the work is based on. So if you have any questions, we'd be happy to take them. Thank you.
Right, excellent. Thank you, Ivan. Thank you for also staying on time mostly. So we are going to move to the discussion now, so to make sure that there's enough time for that. So if you can please stop sharing your screen and let Dan take over.
Yep.
I think that was great.
Okay, let's see. So no, I can't see my screen. Oh, there we go. Okay, great. Thanks very much to the organizers and to Iván for the really nice talk. I want to use my little bit of discussion time to give a kind of summary of what I think the take-home points are, and to raise some discussion points for consideration. So first of all, thanks to Iván. I thought this was a really excellent and thought-provoking paper. And he cites this at the end, but it's worth noting that this paper that he's been talking about here is kind of a continuation or an elaboration of a set of ideas that originated in an earlier single-authored paper by Iván that was published last year. And so in that paper, he sort of introduces some relevant concepts and has a lot of interesting kind of philosophical discussion about the nature of causal influence and interventionism versus non-agency views of causality. And so a lot of the sort of like groundwork is done there. But in this paper, the proposal is sort of elaborated and some new results are introduced. So the specific decomposition that was introduced in that first paper, to begin with, we already knew from that first paper that it has certain desirable properties. And then in this second paper sort of elaborates on those properties and proves some new ones. So the first one is that the decomposition that Iván proposes decomposes the average causal effect instead of some alternative total estimand. So it's the actual ATE, the sort of usual quantity that we begin with in causal inference, is decomposed into these 5 path-specific parameters, including that interaction term. Also proves that these parameters satisfy the path-specific versions of the sharp null criteria introduced by Caleb Miles in recent work, so that they have a kind of interpretation at the individual level as representing certain kinds of causal mechanisms along specific pathways. He also proves that in the absence of intermediate confounding, that the parameters that are proposed here are equivalent to their natural versions. So like the natural path-specific effects along those specific pathways in his decomposition. So that which is a nice property to have, because it sort of says that in the absence of the whole problem that motivated this new decomposition, the problem being intermediate confounding, and it really is a problem. It's a problem that I think is super ubiquitous in applications of mediation analysis. It can really ruin your life or ruin your attempted mediation analysis. And so that was the problem that motivated this decomposition, or at least one of the things. But in the absence of that intermediate confounding, the parameters reduce down to their kind of more natural versions. And then finally, the last part that Iván sort of concluded on is about how this newly proposed estimands behave in the context of separable effects models, where now replacing the kind of cross-world assumption that people have criticized with separability assumptions about the effects along particular pathways, and that you get the sort of similar behavior as you would in the case of natural direct and indirect effects, namely that the quantities are identified by their same identifying functionals, and the cross-world assumptions go away. So I think these are all really nice properties for a new proposed target estimand to satisfy. And in general, Iván's paper raises all these really, I think, interesting and difficult questions about what do we want out of a proposed target estimand. No estimand is going to be perfect. There's going to be pros and cons to any proposal. And so these are the pros. These are, I think, quite important desiderata for any new proposal to satisfy. But there are also some drawbacks or limitations, as for any proposal. So let me talk about two of those. The first one I wanted to bring up is the interpretation of the proposed estimands on an individual level. And Iván mentions this sort of briefly in the earlier paper, but not specifically about mediation, about in the context of the total effects version of these kinds of randomized estimands. But I think it's worth reflecting on. So if you consider one of the effects, the effect along this pathway from A to Z to Y, the natural path-specific effect along that pathway ends up looking something like this, where you're contrasting two nested potential outcomes that differ according to how the intermediate confounder behaves. In one case, it behaves like the treatment was assigned to active value 1, and in one case it behaves as if the treatment was assigned to the sort of reference value 0. And in both cases, the mediator acts like it saw the treatment. So for an individual, you're asked to imagine these two contrasting worlds, in which for that individual, their vasopressin level switches from the kind of like smoker vasopressin to a non-smoker vasopressin. But in both worlds, their blood pressure level is whatever it would have been had they been in the smoking arm of the trial. And that is arguably already kind of hard to imagine, but I think it is, we're sort of used to thinking about these cross-world scenarios. And to contrast that with what we have to think about when we think about these newly proposed effects, in the proposed decomposition, Iván sort of replaces Z1 in the value of the mediator with its recanting, with the corresponding recanting twin, right? So now, again, we're contrasting two potential outcomes where there's a difference between the two that in how Z behaves, the intermediate confounder behaves. But now the mediator behaves in this kind of arguably strange way, where it sort of thinks that the individual is a smoker, so they're exposed to value 1, but then it replaces their vasopressin levels with a random draw from the distribution of Z given A equals 1 and W. So for a particular individual, this number, this T of 1 is just 0 or 1, right? It's a random draw from this, if Z is binary, say, this is like some Bernoulli distribution, and it's a random draw that will be equal to 0 or 1 for that particular individual. Now, I think what's like kind of puzzling or difficult in terms of the interpretation is that this random draw for a particular individual could by chance match the blood pressure level that the individual would actually have had they smoked. So we assume that this thing, the value of Z of 1 for that individual just exists, and it's either 1 or 0 for that particular individual. So the random draw T of 1 could either match that or it could disagree. It could be either 1 or it could be 0. If it matches, then the contrast is just the same for that particular individual as their natural contrast, the natural PSE. But if it doesn't match, it's sort of hard for me to say what is the interpretation of this contrast. You're sort of imagining an individual for whom they would have had like high vasopressin levels if they were smoking, but you're imagining replacing their vasopressin levels with a kind of random draw from this reference distribution. You're asked to imagine quite a lot is different about this world, these two worlds that we're contrasting from what is the natural direct and indirect effects sort of ask you to imagine. I personally find it somewhat hard to articulate what we're exactly comparing here on an individual level. And in fact, and Iván mentions this in passing in the earlier paper, and he sort of warns against thinking about these quantities at the individual level, and rather asks us to think about joint distributions, like the joint distribution of the potential outcome Y and A, the exposure, or Z in this case, the intermediate confounder. And so his earlier paper focuses on functionals of that joint distribution and sort of asks us to avoid thinking about the individual level. But I do think that this means that if we put expectations around these contrasts, which is ultimately what we're estimating, what are we aggregating expectations over exactly, I think is somewhat complicated to understand. And I think that has a consequence of being complicated to communicate to practitioners as well. So that's sort of my main first discussion point. My second discussion point is about the interpretation of the proposed quantities, even as averages, as expectations, when things are not null. So when the proposed effects are null, we know that this means that the corresponding natural path-specific effects are also null. So that's nice. So that means that under the null, this new quantity just agrees with like the old quantity or the classic quantity. But when they're not null, how far the new estimand can be from the natural counterpart is not clear. And assigning specific numbers to this new estimand, so say I estimate that this effect along this particular pathway from A to Z to Y is equal to 0.3, I want to think like, oh, that's like, it's not 0, but it seems like kind of small, as opposed to the estimate being equal to 0.9, that seems somehow larger, still not 0, larger. But it's really difficult, I think, to calibrate in any sort of external way, like how much larger than 0 is 0.3 or 0.9, and what is the difference between these two specific numbers. My guess is that so in the earlier paper, Iván has a result when he's talking about a particular estimand that kind of operates in a similar way to the one proposed here, where he relates that new estimand to what the average treatment effect looks like. And there's a kind of scaling factor that relates the new estimand to the kind of classical average treatment effect. And there's no result like that for these more path-specific estimands. My guess is that the reason for that is that whatever scaling factor relates the new path-specific estimand to its natural counterpart is going to depend on this non-identifiable quantity, which is about the kind of cross-world recanting witness issue. And so we don't know, we can't calculate this thing, because if we could, then the original path-specific effect would just be identified. But there's some sort of scaling factor. How big or small that scaling factor is seems to depend on features of the data generating process that are unknown to us. And in particular, I conjecture that whether it's smaller or bigger than the natural counterpart will depend on the problem. More importantly, I think this has implications for how we should compare the relative magnitudes of effects along different pathways. So say we estimate non-null effects along two different pathways that are of interest, the pathway through Z and the pathway through M. We see that they're both non-null, and we want to be able to use these estimates to say something about whether one path is stronger than the other. But I think without knowing something about how to interpret the particular magnitude of these effects, it's hard to say whether one pathway is really stronger than another. It would be interesting if there was some sort of monotonicity preservation, so that where we can say something like, if path 1 is stronger than path 2 as measured by this new estimand, then path 1 is also stronger than path 2 as measured by the natural path specific effects. I don't know if that's true. Maybe it is. Maybe that's something that can be proved. But in any case, I feel like this leaves a kind of like open question about how we can actually apply the proposed quantities for comparing the relative strengths and magnitudes of path-specific effects. Which is not to say that they're not useful. I think they are very useful for determining the existence and sign of an effect along a particular pathway. But in terms of the magnitude, it seems at least that there's some open question here. So a possible procedure you could have in mind, using the apparatus that Iván has introduced, is to first test for the presence of intermediate confounding using the test that he proposes, this interaction parameter, which vanishes under the null of no intermediate confounding. So you can estimate that thing, test whether it's 0 or not. And then if intermediate confounding is not detected, you may want to proceed with estimating natural path-specific effects, because in that case, they're identified. And if intermediate confounding is detected, then you can estimate you can estimate the proposed quantities, at least to evaluate whether the effects along particular pathways are non-null, and what is their sign? Are they in the positive or negative direction? But without taking too seriously the magnitudes of those estimates. This procedure raises its own issues about, you're testing a null hypothesis of 0 intermediate confounding. You may consider alternative versions of testing that maybe use a kind of equivalence test formulation. You also have a kind of post-selection issue if you do this kind of procedure. But I think this is at least a very sensible way of trying to apply some of the apparatus that Iván has introduced. So I'll conclude there. I'll say again, congratulations to Iván and co-authors on this exciting work. I think it raises a lot of deep and foundational issues about what we want out of mediation analysis and various measures of causal dependence or causal influence that could be proposed. And it satisfies certain desiderata, certain properties that are nice, but it might not satisfy everything that we want. And I think it is fully possible that no causal estimand or quantity that anybody proposes will satisfy everything that we think we want out of mediation. Maybe it's just hard, or what we want is not mutually satisfiable. But finding quantities that serve particular purposes, I think, is an admirable and more feasible goal. And I think that this work is a really nice step in that direction. So I'll conclude there.
Awesome. Thank you, Dan. And I mean, I can sit here and listen to the two of you talk about this, for a very long time. Unfortunately, we are out of time. At the same time, I don't want to just leave all these remarks unanswered. So Iván, if you can give Dan a short answer to what he's talking about.
Yeah. So I'll try to be brief. Yeah, I mean, your point one, Dan, I completely agree. When we have, we have to give up on the natural path specific effects, and by giving up, we have to something has to fail, right? And the what you discussed for your discussion point one, I actually think it's a feature of stochastic interventions in general. When you intervene by doing a random draw from something, you lose a lot of the individual specific effect. And so I think I completely agree that that's a feature of this, and I don't know that we can that we can solve that. For your second point, and so I agree with the just the first point. The interpretation is at the population level, as you mentioned, and I tend to see these interventions more as a way of measuring functional dependence, right? Like if you look at the structural causal model and you want to study, does this function depend on its argument? Then the stochastic interventions allow you to study that in some way. But yeah, individual effects, I think we have to give up on. Your second discussion point, thanks so much for bringing that up. That's something that we have not considered, and I do think it would be nice to prove that to take a look at whether these path-specific effects preserve the order of the natural specific effects. And so that's definitely some work that we have to do there. Again, it would be another property that it's along the lines of what you said, like there's a number of things that we would like for this to satisfy, and that's, I think, an important practical one that we'll take a look into. And the third point is, I think, yeah, your proposed approach for testing and then deciding what to estimate in response to the test may not be necessary, actually, because what we show is that under no intermediate confounding, the path-specific effects are equal to their natural counterparts, right? So you can just directly go and estimate these quantities that we proposed and use the test more as an interpretation device, kind of interpret them as am I allowed to reject the interpretation of natural path-specific effects versus not? Yeah, and I'll leave it at that.
All right, thank you. Thank you both. Thank you, Ivan, for the talk, and thank you, Dan, for the presentation, for the discussion, and thank you for keeping the response short. To wrap up, I'm just going to quickly close this seminar. Next week, we have Maria Glimmer from Boston University and Serena Gutierrez from UCSF, University of California in San Francisco. So we hope to see you there.